Okay, so tonight, this is already up. So it's up on the blog. You can check that out later if you like. If we look at this, that's incorrectly wrong.
Is it 39 or 59? Because before it says 59.
Oh, whoops, just kidding. It's supposed to be 59. Good call, thanks. How'd you know that?
I'm bored.
Oh. How did you get up there? Did you do that?
What?
Put it up there?
Put what? I haven't written anything on the board.
Holy crap. Way to go. Alright. Okay, for the pendulum, if this is hanging here, right, the gravity is g sine theta and all that good stuff. In order to do this, we have to use something called the small angle theorem. You know this from math, right? It says for small theta, theta is approximately equal to sine of theta. Right? So here, that means the sine of theta for this triangle here is S over L. So therefore, theta is S over L. And how that helps us, it comes out to something like, we know that the acceleration, we already figured that out, was g sine theta. And depending on your frame of reference, you could say negative, you could say positive, however you want to do that. Like if it's swinging up, I think you can see that's going to give us a negative g sine theta. And then from that, we can say negative g theta. And so we can say A is negative g s over L, which is the same as saying g over L times s. Okay, now, do you see that this, right, which is d2x over dt squared, this looks the same as what we got when we derived the other one. When we got the acceleration of the other one, we got negative k over m times x. So this part right here is similar, right? And then from that we can do a couple things. We can say a couple things. We know. So we know that that's telling us that this is going to behave like the spring, that it's oscillating harmonically. We already knew this from our observation, right? We looked at both things, saw that the acceleration was proportional. We saw that g sine theta changes as a function of displacement, so we knew that both were harmonically oscillating. And then, yeah.
How did you get from G over K over M?
How did I get is G what?
That's just first spring.
Oh, this is from the spring. That's from our knowledge of the spring. Here, let me go ahead and try to, running out of time, damn it. All right, I'll try to flesh that out though so you can see a little more. If we, let's see, maybe if I do like, you remember what I said x of t is this a cosine omega t, and then dx dt was negative omega A sine omega t, and then d2x over dt squared is this. Right, from this, if we say this acceleration is the same, we can look up here and cancel this out. You see that? So we know this is acceleration. So that means acceleration is negative omega squared times x. Right? And then from our original thing, we said that omega was the square root, oh god, that's weird, of m over k, right? Remember that? That was from the first derivation? What's that? Yeah, it's possible. And then what I'm saying here is that this is m over k times x. So this looks just like our previous window. That's how we got there. So it's negative j over L times s, negative k of m times x. And then from that, we know that it operates the same way. So the final result is that you get, I have 10 things. The final result is that you get the period is 2 pi square root of L over G. And that's because T is 2 pi, omega is 2 pi over T, so T is over this, right? So then that's 2 pi square root of L over G, because omega is G over L. All right, you need to be able to do both of those derivations, so work on that. And this is